Fascinating Frontiers, Episode 46, March 28th, 2026. Runtime, approximately 15 minutes. Hey everyone, thanks for tuning in to Fascinating Frontiers. I'm Patrick, coming to you from a drizzly Vancouver morning, and I'm genuinely excited to share what's been happening out there in the cosmos and closer to home this week. We've got stories that stretch from the harsh realities facing rocky planets around red dwarfs all the way out to the rings of Saturn, and even a possible echo from the very first moments after the Big Bang. Let's dive in. One of the most thought-provoking pieces of research that crossed my desk recently looks at how quickly a Mars-like world orbiting an M-dwarf star can lose its entire atmosphere. The modeling focused specifically on a hypothetical rocky planet circling Barnard's star, that famous fast-moving red dwarf just 6 light-years away. What the simulations show is sobering. The atmosphere could be stripped away in only a few tens of millions of years through aggressive atmospheric escape. The team modeled 2 main culprits working in tandem. First, the intense ultraviolet and X-ray radiation pouring out of the cool but magnetically hyperactive star heats the upper atmosphere until gas molecules gain enough energy to reach escape velocity and simply drift off into space. Then the stellar wind itself acts like a relentless cosmic sandblaster, with high-speed charged particles physically knocking atoms and molecules away from the planet. This is the same basic process that turned ancient Mars from a world that once had rivers and lakes into the dry, thin atmosphere planet we see today, but it happens far more violently around smaller active M-dwarfs. What really stands out to me is how long these red dwarfs keep their magnetic activity turned up to 11. While our sun calmed down after its first billion years or so, many M-dwarfs stay magnetically noisy for billions of years. That means the erosion doesn't let up. A teaspoon of the dense plasma in those stellar winds can be moving at hundreds of kilometers per second, carrying serious momentum. The result? Thick atmospheres can vanish in what amounts to a geological eye blink. We already see this process in action. Telescopes have watched hydrogen and even heavier elements leaking from hot Jupiters and a handful of rocky worlds during transits. Yet here's the lingering mystery that keeps researchers up at night. Why do some small planets around M-dwarfs manage to cling to thin atmospheres while others orbiting at almost identical distances end up completely airless? Different compositions, magnetic fields of their own, or maybe just luck in the timing of stellar flares. It's a puzzle. The takeaway for me is that we now have another crucial filter when we evaluate potentially habitable exoplanets. It's not enough to be in the habitable zone where liquid water could exist on the surface. We also have to ask whether that world can hold on to its atmosphere long enough for interesting chemistry, let alone life, to take hold. This work adds real depth to how we'll interpret the next wave of discoveries from the James Webb Space Telescope and future observatories. And just to give you a sense of scale that still blows my mind, if you shrank our sun down to the size of a grapefruit, Barnard's star would be about the size of a cherry tomato. Yet that little star can strip atmospheres far more effectively than our larger, calmer one. It's a beautiful reminder that in space, size isn't everything. Speaking of worlds we actually have a shot at visiting soon, things are picking up pace with NASA's Artemis program. The 4 astronauts who will fly around the moon on Artemis 2 arrived at Kennedy Space Center on March 27th for the final stretch of preparations ahead of a possible launch as early as April 1st. This mission will mark the first time humans have left low Earth orbit since Apollo 17 more than 50 years ago, and it's going to be an absolute thrill to watch. Supporting the communication side of that flight is Eric Richards, the Near Space Network mission manager. What I love about his story is how it quietly connects decades of experience in some of the most remote places on Earth, including Antarctica, to the deep space challenges of talking to a crew flying past the moon. These long, steady careers often don't make the headlines, but they're exactly what makes ambitious exploration possible. It's the kind of behind-the-scenes dedication that always leaves me feeling optimistic about what we can achieve when smart, patient people keep showing up. While the Orion spacecraft prepares to fly free, NASA is also making sure we get more science onto the actual surface of the moon. The agency just signed a $180.4 million contract with Intuitive Machines of Houston to deliver 7 payloads on a future commercial lander. 5 of those instruments are funded directly by NASA, and together they'll help us better understand the moon's chemical composition and internal structure. This is all part of the steadily growing Commercial Lunar Payload Services Program, or CLPS. I find it really encouraging to see how commercial companies have moved from being occasional helpers to becoming essential partners in lunar exploration. Every successful landing builds confidence, lowers costs, and lets scientists focus on the questions rather than the rocket science. It feels like we're watching a genuine ecosystem take shape. Of course, not everything in the Artemis world is moving forward smoothly. Following NASA's recent decision to pause work on the Lunar Orbiting Gateway Station, the European Space Agency now has to completely rethink its contributions to the program. ESA is expected to make a formal decision by June, and that choice will significantly shape Europe's role in Artemis going forward. It's a reminder of just how interconnected this international effort really is. One partner's budget reality ripples through everyone else's planning. I'll be watching closely to see how Europe pivots, whether they double down on surface elements or find new ways to contribute from orbit. Back in low Earth orbit, NASA is also getting ready to fly a bunch of new technology and science demonstrations on the upcoming SpaceX Transporter 16 rideshare mission aboard a Falcon 9. These payloads will test next-generation thermal protection systems, experiment with improved in-space communications, and carry instruments to study Earth's atmosphere from above. Rideshare missions like this have become such a reliable workhorse, quietly delivering practical advances that benefit everything from satellite design to future crewed exploration. It's the kind of steady, unglamorous progress that compounds over time. While those experiments look down at Earth, another group of scientists is looking up at where we hope to walk next. 10 participating scientists have been selected to help shape the Artemis Lunar Surface Science Plan, with a particular focus on the South Polar region. Their expertise will guide where instruments are placed, what observations the astronauts should prioritize, and even how future crews collect and document lunar samples. The South Pole is one of the most scientifically promising places on the Moon, with its permanently shadowed craters and potential for accessible resources, so having sharp minds focused on the details now feels like smart preparation. And speaking of resources, one of the most important questions at the South Pole is how much water ice is actually there and how accessible it is. NASA is preparing a neutron-based instrument that can detect hydrogen and therefore likely water ice, up to about 3 feet underground without any digging at all. It's such a clever, non-invasive way to map this critical resource. Finding usable water near the lunar South Pole would be a game changer because it could provide drinking water, oxygen, and even rocket fuel for future missions. That single discovery could turn short visits into something much closer to a sustained presence. Shifting our gaze from the Moon's future to the more distant past of our own solar system, new computer simulations have strengthened the idea that Saturn's spectacular rings formed from the debris of a lost moon the researchers nicknamed Chrysalis. The model also offers a neat explanation for why Saturn is tilted the way it is today, and why its rings appear surprisingly young compared to the planet itself. These kinds of sophisticated simulations keep showing us that our solar system has a far more violent and dynamic history than the neat diagrams in textbooks suggest. Moons colliding, migrating, and being torn apart, it's cosmic drama on a grand scale. Even farther back in time, possibly all the way to the universe's earliest moments, there's an intriguing new gravitational wave signal that has astronomers talking. LIGO recorded an event on November 12, 2025, coming from an object smaller than our Sun. 2 astrophysicists have put forward the idea that this could be a primordial black hole, a type of black hole that would have formed in the extreme conditions right after the Big Bang, long before the first stars ever shone. If that interpretation holds up, it offers an extraordinary window into physics we simply can't recreate in any laboratory. It might even help answer some of the deepest questions we have about what happened in those first fractions of a second after the universe began. The possibility alone gives me chills. Much closer to home, plenty of people have been enjoying a recent uptick in bright meteors visible over Ohio, Texas, and parts of Europe. The good news is that the increase seems to be driven more by greater public awareness and easier ways to report sightings than by any actual surge in meteor activity. I love that more people are looking up and sharing what they see. Every fireball report helps us refine our understanding of where these rocks come from and how often they intersect Earth's orbit. It's citizen science at its most accessible. Meanwhile, satellites continue to give us stunning new perspectives on our own planet. The joint US-Indian NISAR mission recently imaged Washington's Mount Rainier using its L-band synthetic aperture radar. Because radar can see straight through clouds, the satellite is especially valuable for monitoring surface changes in the Pacific Northwest, whether that's tracking glacier movement, volcanic deformation, or landslide risks. This kind of consistent all-weather Earth observation is going to become even more important as we try to understand and adapt to our changing climate. Finally, a couple of quick but encouraging updates from the commercial space sector. The Commercial Space Federation recently welcomed two new associate members, Astrolab, which is working on advanced planetary mobility systems, and Power, which is developing reliable power solutions for extreme environments. Both technologies could prove vital for long-term operations on the Moon and eventually Mars. It's exciting to see specialized companies focusing on the nuts and bolts challenges that will make sustained exploration possible. Before we wrap up, I'll just say keep an eye on how ESA's decision in June about the Gateway Station plays out. It could quietly reshape everyone's role in the Artemis program for years to come. That's it for this episode of Fascinating Frontiers. If any of these stories caught your imagination, please share the episode with someone else who loves looking up. I'm Patrick in Vancouver, wishing you clear skies and curious minds. I'll talk to you again very soon. This podcast is curated by Patrick, but generated using AI voice synthesis of my voice using ElevenLabs. The primary reason to do this is I unfortunately don't have the time to be consistent with generating all the content and wanted to focus on creating consistent and regular episodes for all the themes that I enjoy, and I hope others do as well.
Drifting softly through the